My name is Felicia Persaud, and I am a hydrochemist at the Hydromet Service, Ministry of Agriculture, and I work in the water quality lab. So my presentation is all on water quality. So the title of my presentation is Water Quality Trends and Observations within the Barima and Lower Kaituma River. The outline of my presentation will take this guide. I will be looking briefly at the Barima-Mora River Basin itself, the hydrological aspect of it. We'll be looking also at soil classifications within the basin, how we went about selecting our sample points, chemical observations and trends that we found within both the Kaituma and Barima River, and what does those findings actually say to us when you compare it against environmental standards. Conclusions that can be drawn. We'll be looking briefly at some instruments and any follow-up questions, if there's any. Okay, it doesn't want to move. Okay. All right, so when we look at the Barima-Mora Basin, we need to consider also the hydrological framework within the basin, because the hydrology can tell you a lot of things about the sedimentation patterns, pollution sources, and the trend in which pollutants might underwater flow act within our river basin. So all of this is the hydrological network. We also identify from previous presentations that there's a lot of communities or streams or those things within the Barima-Mora Basin. But we want to focus mainly, I just want to identify a few things that I want to focus on mainly within my presentation, which is the Mora Passage and where exactly it's located. We also have the location of the Kaituma River and also the location of the Barima River. So one other thing when we talk about water quality, we need to consider the soil composition or the geology of the basin. So when we look at the soil composition within the basin, we identify that there's approximately about 6 different types of categories within the basin. But most importantly, we find that where our samples were collected from, it's mostly situated in the area we have ester soils, or the soils are classified as ester soils. But the river also runs between the earthic aquasoils and also the litter soils, right? But our main focus area is more so at the mouth of the basin. So when we look at the characteristics of ester soils, see that ester soils is most like an organic soil. It's formed basically through the decomposition of organic material soil within that basin. And also, with that being said, it can also give the water a low pH characteristic. So the methods that we employed when we went and did our sample collection. So we actually used where we saw camera traps, use that as a guide to place our sample point. So that's where we kept the study area or our sample points within the study area where they had the camera traps for the mammals. So we had about 19 sample points within the Barima Basin. Just for you to see it a bit better, we had 19 within the Barima Basin. And within the Kaituma, we had roughly 9 sample points. So those sample points were approximately 2 km apart also. So some analysis that were done within both the basin. The analysis were done within 2 years' time. We had 2 days of analysis to complete, 2 days to complete the analysis between both the Barima and the Kaituma River. So that's why we have pH in the year 2021 and in 2022. So we're going to look at the characteristics or the pH between the 2 rivers. So the first one is the Kaituma River. We see that for in the year 2020, okay, let me just pedal back a little. So 2 types of analysis or interpretation we're doing here. We're looking at how the parameters move along the stream from the source of the river to the mouth, or from downstream to upstream, and we're also looking at the general characteristics a bit later down. So for this one in particular, we're looking at when the sampling went from downstream to upstream, so moving from sample point 20 to 28. So we see that from the year 2022 and 2021, we had a slight decrease in pH content as we moved from 2021 to 2022. However, we would say that for 2021, it was a bit more better to some degree, but also even though there's a variation, there's not much variation between the 2 years for pH content within the Kaituma River. For electrical conductivity, we saw a similar trend where there was a gradual decrease for 2022 and 2021. Although there was a slight decrease, we also saw slight decrease or reduction. It also increased as we went from sample 20 to sample point 28. And we see that throughout that for all the parameters as we measure them. So we also measured dissolved oxygen content. There is not much variation between the 2 years, but it was also observed that it was low, which was a surprise to us. For the nitrate content, we also expect a low nitrate content within the basin. We also found as the year 2021, we had the highest concentration, but as we moved down, we also had low concentration. But in 2022, we saw it was a bit more constant within the Kaituma River. When we look at the Barima, we had a similar trend also with the Barima River pH. It started almost neutral, but then it dropped to something being slightly acidic or moderately acidic within both years. The conductivity value of it with the Barima was much more lower than the Kaituma. However, at our 4 sample points, we had a very large increase, and that was mostly to the mouth of the river. And here also we had the 90 sample points, which is way more than what we have in the Barima, in the Kaituma River. For the total dissolved oxygen, we had similar trends also when compared to the Kaituma. Again, it went between a range of over 0.5 to just over 2 milligrams per liter in concentration for dissolved oxygen content. And for the nitrate concentration, again, we saw for this particular basin, we had much more nitrogen concentration within this particular basin. So the reason for these we're assuming is because we have runoff from land and so forth, because even our sample collection, we had a rainfall and those sort of things. So we could be assuming that because of those natural events, it caused the nitrate concentration to be high within this particular river. So we try now to actually give an overall assessment of the basin. What we did is actually find the averages of each parameter between the 2 years. So we have in the blue, we have year 2021, and in the red, we have 2022. So we compare the pH value, the EC value for Kaituma for the year 2021 to 2022, we didn't find much variation within those with the EC content. However, with the Kaituma, we saw there was a large drop in the EC concentration as we moved from the year 2021 to 2022. Okay. Dissolved oxygen concentration, again, there's not much variation within the basins and within the years that we collected, but for 2022, we also saw a spike within the dissolved oxygen concentration content from within the rivers. Nitrate, similar observations were observed or found. In the year 2021, we have a higher concentration of nitrate, and 2022, there was also a drop in concentration of the nitrate. When we look at the pH values now, we see that there's not much variation, but there was also a slight increase for the Barima River, but the Kaituma River, it was an inverse relationship. So what does that all basically say to us, what can we draw from those data we actually collected? So when compared between the years, we saw there was not much variation observed between the tested parameters with the exception of nitrate, which had increased in 2022. So if you have an increase in nitrate concentration, although for the US standard, US EPA standard, they have a limitation of 10 milligrams per liter of nitrate in surface water. For us, ours was around 6. For the IS, it went from approximately like a 3 point something to a 6, approximately there. So although we're not over the limit, we're under the limit, we still see an increase. So we still want to keep continuous monitoring to make sure that this particular parameter doesn't exceed or goes beyond that limit and cause a problem, as we know, as eutrophication, which would cause not an issue or implicate or decrease the dissolved oxygen content concentration even further within the rivers. So again, neutral water, we want it to be between a pH of 6.8 to 8.5, but ours was approximately around 5 to 6. So although there's not much concern with that, it's not a major concern for environmental concern at this point in time. The only thing is that within the environment itself, we know that that basin, the soil type within it is actually an acidic environmental condition due to the organic matter within the rivers or within the basin. But we still want to keep monitoring and make sure that it's within those limits and it's not beyond or below that, which would be a major cause of concern. So when we look at the dissolved oxygen concentration, we know that the dissolved oxygen concentration, we want it to have at least a limit between 5 to 8. That is the conditions for a good aquatic environment. So when it's below those values, we see that it places a lot of pressure for the aquatic animals that's actually within those rivers. So because some animals also can live or survive under those stressful environments, but if it continues, then it could actually be a bit more detrimental. So we don't want our dissolved oxygen content to decrease any further, but at this point, it's between, I believe, 2 milligrams per liter for dissolved oxygen concentration. I keep blanking it out. Okay, and we see that the only variable that we tested that was actually within, you could say, a pristine environmental condition was our electrical conductivity. It had less than 100 microsiemens per centimeter that was found for both basins when we compare it, but we want to keep it, those are conditions that's actually suitable for certain animals also, but that was the only parameter we found that was suitable for aquatic animals during our investigation. So one other thing we want to mention is that because our exercises were just 2 days for each year, just to make sure that we understand fully all of the implications or the factors that can affect our parameters and so forth, we would like to speak about having more continuous monitoring within that area so we understand a great deal more what exactly is affecting our parameters and what exactly is causing our parameters to vary that much, if it's just the rainfall, if it's surface runoff, if it's other environmental activities within the area. So continuous monitoring is encouraged. And this is just some of the instruments that we used on our exercise. We have our turbidity meter. Although I didn't mention anything about turbidity because we just did the turbidity measurement for 1 year, but the following year we didn't have the capacity at the time to do the turbidity measurement. But this is a meter that we use in the fields to measure the physical, not the physicochemical, the in situ parameters, and our nutrient parameter was measured with the HQ40D probe multimeter, which was used to measure the nitrate concentration. And our YSI Pro 1030 was actually used to measure conductivity, TDS, and so forth. This is just some pictures on the field assignment there, where we went and collect the camera traps, I believe, and also water quality monitoring. So, yes, I also have my other colleague there, Sharon the AGARD, who was on the first assignment with me, and the other team from GMCS. Yes, and that's the end of my presentation with respect to water quality within the Barima and Kaitumo River. Any questions?